everyone, I'd like to talk about an advanced example in cylindrical coordinates. So before we begin, let's just remind ourselves that when we're talking about cylindrical coordinates for an integral, a triple integral, we are talking about integrals involving theta, z, and r. So theta is some angle, z is our height up and down the z-axis, and then r is some sort of radius. And when we have these integrals, we start working on them from the inside out. So if I were going to compute an antiderivative, I would be first looking in here in my innermost integral and integrating with respect to whatever the variable is. The most important thing to remember, and the thing that a lot of people forget, is that when we're setting these up, we have to include r times whatever function we're integrating with respect to. So when you're converting from Cartesian to cylindrical, you have to introduce this factor of r. So I always remind myself and remind my students, don't forget your r. Okay. So let's take a look at an example. In this example, I'm going to suppose we're given some information, and the information that we're given is the following. So I'll say this is example one. We're given some information about mass. So we're told that mass is density times volume. And so if we start to think about this as a differential, we can think about the change in mass is some triple integral of our density function with respect to volume. And that kind of makes sense theoretically, but when it comes time to actually setting up a model and computing it all, it takes a little bit of thought to figure out how to set everything up. All right, so that's our general framework. We're given a little bit more information. So for this problem, we're given some information about a cone. So I'm going to draw a cone here. And the height, I'm just going to put an axis in here for us. So I'm going to suppose this is our z-axis, and that z-axis is going right down through the center of the cone. So I'll label that z. And then, of course, you could have a y-axis and an x-axis kind of coming out of the paper at you. And I'm not going to worry too much about the x and the y, simply because I'm not going to work on this in Cartesian coordinates. I really am thinking about r's and z's and thetas. So that's why I'm very interested in the z-axis. Now, some information that I know about this problem. What I know is that when I'm up at the top of this cone here, when I'm way up here, my radius is 4, and the height there on the z-axis, that would be a z of 5. And then this outer edge on the cone here is kind of a weird, let me make it a different color. Make it even a little bit bolder. This slanty edge there of the cone, it's going to be different at different heights. If I had only moved up to, 1 unit instead of all the way up through 5, I'm going to have a smaller little slanty edge out there compared to this full slanty edge when I'm at the maximum position on my cone. But I need some sort of variable to represent this slanty edge out here. You could call it some other radius. It's a little bit confusing. I'm going to call it rho. So rho is a Greek letter. It looks like a curvy P, but it's rho. So there's my P and there's my rho. I'm not talking about P, I'm talking about rho. Now, I don't know much about rho, but I can see that I have a right triangle in here. So if I wanted to set up an equation here, I could say that, use a different color, I could say that r squared plus z squared equals rho squared. In other words, if I solve for rho, I would get plus or minus, and since we're talking about the length of the side of a cylinder, I definitely don't have the minus sign going on. I can just worry about the positive root. Okay, so that is very, very helpful for us. So this question, what about our density function? Well, we have some information that's given to us in the problem. So this was given. If you're wondering where I got that from, that's given to us. So density as a function of rho equals 3 plus 2 times rho. And we can plug in what we know about rho. I know something about rho right down here. So my density function is really 3 plus 2 times the square root of r squared plus z squared. So now we've got a lot of ingredients. I can make that replacement for what I know about our density. I won't forget my r, so that's there. That's good. There is a little bit of work that you will need to do to figure out your lower limit of integration for z. I'll let you work on that, but this gives you some ideas for getting started.